This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Right, I had trouble getting through all my slides, so we'd better get started. And to establish my credibility, no chemistry teacher should have any right to teach chemistry if they can't sing the periodic table. Wouldn't you agree? So you haven't got a bouncing ball for you to follow, but you can pick it up if you like. There's antimony, arsenic, aluminium, selenium, hydrogen and oxygen, nitrogen and rhenium, nickel, neodymium, neptunium, germanium and iron, americium, ruthenium, uranium, europium, zirconium, tritium, vanadium, lanthanum and osmium, astatine and radium, gold and protactinium and indium and gallium and iodine and thorium and thulium and thallium. There's yttrium, terbium, actinium, rubidium and boron, gadolinium, niobium, iridium, strontium and silicon and silver and samarium, byzantium, lithium, beryllium and barium. Don't you find that interesting? Why aren't you taking notes? It's on the exam. There's holmium and helium and hafnium and erbium, phosphorus and fluorine, francium and terbium, manganese and mercury and molybdenum and magnesium, dysprosium and scandium and cerium and cesium, lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, technetium, titanium, tellurium, cadmium and chromium and calcium and curium. There's sulfur, californium and fermium, berkelium and also mendelevium, einsteinium, nobelium, argon, krypton, neon, radon, xenon, zinc and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered. Okay. Well, I hope that's established my credibility, so let's get going. In your booklets, you've got some websites. If you don't know about VCAR, you're probably behind the times. But the CEA, you may not have been aware of. That often has more stuff on old exams and advice and things. There's a lovely app you can put on your iPad or your iPhone. I think it works on an iPhone. A spectroscopy revision, for those of you who just love spectroscopy, can't get enough. And there's ATAR notes. There's Scotch Snots and Melbourne High and all those really super bright kids, but Kwong is probably on there already. Often blog each other about really weird and obscure questions that are sometimes a bit frightening. A bit of general revision. There's lots of work. A lot of you have checkpoints, but there's a lot of commercial material out there trying to slug money out of you. So if you can get hold of free stuff from there, that'd be great, but otherwise it's quite expensive. And then we want to get down to as many practice exams as possible, preferably 2.5 hours. So let's have a quick look at what's available. Keeping in mind some of the history. Whoops, where's this going? I've lost my mouse again. Oh, damn it. All right, so there's a new study design that's come in last year, you're probably aware of. The previous one came in 2008. So last year it didn't change much from 2008. So practice exams going back to 2008 are probably still mostly relevant. Come on. But in terms of VCAR stuff that's super relevant, you've got a sample exam that they put out last year. You've got last year's November exam and this year's Northern Hemisphere timetable. Have you all heard of the Northern Hemisphere timetable? It can be quite hard to find on the VCAR website, but it's there if you search hard enough, but the answers aren't up yet for this year's exam. But anything past 2008 is still mostly relevant, but the 2.5-hour exams only started in 2013. You may be aware of that. So before it, there were 1.5-hour exams in June for Unit 3 and 1.5-hour exam in November for Unit 4. So on the website, I don't know why I've lost the mouse. No, it's gone. So there's the VCAR website, but CEA You can go back to 2000 with all the exams, and they've got the sample exam, and they've got answers for the sample exam. So that's probably worth reviewing that side if you're not familiar with CEA, the Chemistry Education Association. The VCAR website, well, you'll see something like that. So 2013 to 2016, 2.5-hour exams. They haven't got some of the new stuff, but most of the stuff there is still relevant. And you've got the examination reports. I sometimes like to think, or it certainly was true in the mid-2000s, that if they found a difficult question, they would often revisit it the next year. I used to call them jugular questions, as if the examiners were going for your jugular because they found out something you couldn't do. So if you read the examiners' reports, you can find out which questions were particularly badly done, because often the next year they revisited it. So I'd go back to last year's exam, see what the examiners said was really hard last year, and you may well find that it gets revisited this year. Now, there are some, I sort of mark exams, and it's really disappointing sometimes that some students lose so many marks just carelessly. I'm sure your teachers have badgered you about significant figures, and usually that's easy, but I might just cover a couple of aspects that often teachers don't cover. Units, again, isn't usually a problem. If you get in the habit of always giving a unit at the end of a calculation, you should be okay. So I've got my little acronym, SUBS, 4 things that you check. SU for calculations, check sig figs, check you've got a unit. If a question says, give the mass in grams, then you can just give any answer and they'll assume it's in grams. But if it just says give a mass and you don't give a unit, then you'll definitely lose a mark. Or if you give the wrong unit, you'll always lose a mark. And there are no half marks, so that can be quite expensive. So if you lose a mark for sig figs and you lose a mark for units, there's 2 marks you've just blown. If you were here for Unit 3, we talked a bit about balancing equations. Often equations are only worth 1 mark. So if you don't get it balanced, it's worth nothing. No half marks, so just double check any equation you write balance and make sure you do symbols of state. Every equation must be balanced. They're only going to check 1 equation for symbols of state. Sure as hell, it'll be the one you forgot to put symbols of state on. So get really paranoid. Oh, I've just written an equation. Check that it's balanced. It's easy to think you're right without actually checking the balance. And it's very easy to forget the symbols of state. Probably won't be half equations in redox, usually only overall equations, and very typical for combustion equations. So we talked about that in Unit 3. Now, the significant figures. If you had something simple like the mole of potassium hydrogen sulfate in 4.08 grams of potassium hydrogen sulfate, then 4.08 is obviously 3 significant figures. But you're going to put that over a molar mass, and you get that from the RAMs in the periodic table in your data book. So there's an addition-subtraction rule, which often doesn't get emphasised much, but when you add numbers or subtract numbers, then the accuracy is determined by the number of decimal places. And all your RAMs are to 1 decimal place, so whenever you add up RAMs, your answer is always to 1 decimal place. So you might notice hydrogen is 1.0 in the KHSO4, and technically that's only 2 sig figs. But it's accurate to the first decimal place. When you add it to all the others, you end up with 136.2, and that is accurate to the first decimal place and now has 4 significant figures. So although the hydrogen only had 2 significant figures, the relative mass now has 4 significant figures. Understand the addition-subtraction rule? And then when we use that to calculate the mole, 4.08 divided by the 136.2, 9 times out of 10, that's all you have to worry about. The 4.08 is 3, the 136.2 is 4. Your answer is going to be accurate to 3 sig figs. Just don't truncate. Do you see the last line there? I can't, for some reason, use the mouse on it. The mouse has died. Don't truncate. So on your calculator it's saying 0.029956. Quite a few students, you'd be surprised, know it has to be 3 sig figs and just chop off the 5 6. That's called truncation. That gets punished. That costs you a mark. So round it off correctly, and the correct answer for this one should be 0.033300. The last 2 zeros are significant. The first 2 are just marking where the decimal point is, so they're not significant. However, that will get you through 9 times, maybe even 99 times out of 100. But here's a couple where I suspect if they did choose to check sig figs on either of these calculations, I could pretty much guarantee 80 to 90% of students would get it wrong. Let's see why. I want to know what mass, so a limiting excess question, what mass of oxygen would be left behind? Okay, so it's kind of telling you the oxygen's in excess. If 9.72 grams of Al, 3 sig figs, is reacted with 10.0 grams of oxygen. So most students are going to think, right, the data has got 3 sig figs, the answer should have 3 sig figs. Am I right? But follow it through and you see you calculate your mole of aluminium, you calculate your mole of oxygen. I've got 2 different ways of getting the final answer. So if we go down the left-hand route, we work out the mole of oxygen that's reacted, we get the mass of oxygen that's been used up, and we get 8.64 grams. Then to get the mass of oxygen remaining, you subtract the 8.64, that's 3 sig figs, from the 10.0, that's 3 sig figs. But the 10.0 is only accurate to the first decimal place. So although your calculator is saying 1.36, your answer is only accurate to the first decimal place because you've done the subtraction. Subtraction rule kicks in, so your answer should be 1.4 grams, not 1.36. Now, would they check that sort of calculation for sig figs? Probably not, but the chief assessor sometimes gets devious and it just might arise. And you'll see the same logic applies down the right-hand side. If you worked out the mole of oxygen that reacted, it's 0.3125 to 1 more sig fig than I'm entitled to, but I didn't want to round off too early, and I certainly don't use a rounded off number in any calculation. I subtract the 0.270, and I note both of those numbers are only accurate to the third decimal place. And when I do my subtraction, the third decimal place is the 2 in the 0.0425. And that's now down to 2 sig figs. So when I calculate my mass of oxygen remaining, I take that mole, multiply by 32.0, but my answer is only accurate to 2 sig figs. So again, whichever logic you go, that would be tough, would you agree? Most students would give it to 3 sig figs. That's not very likely. You don't get many limiting excess calculations, and even when you do, it's not usually how much of something is left over. So there's not usually a subtraction involved. More question?
If you have like this multiple part question, and then for like part A you get 1.4, do you use the rounded figure for the next part?
No, never ever use a rounded off number. So you've just got a number, you've rounded off correctly, but it's on your calculator. You know you need it for part B, leave it on your calculator. If you've lost it, put it back in. Yep, put the original data back in so you've got the full unrounded number on screen. Look, your chances of getting pinged are not great. You'll probably get away with it. They often allow you to use a rounded off number. But if it ends up being out of range, they'll have a range for the final answer that's acceptable, that usually allows for putting back in rounded off numbers, but not if it's too heavily rounded off. Yep, so, yeah, look, the safest thing is never use a rounded off number. Just leave it on your calculator in the unrounded form and keep going with it. And that's quicker than putting it back in anyway, usually. All right, more likely to happen is when you've got changes of temperature in calorimetry, because then there's definitely a subtraction there. You've got an initial temperature, you've got a final temperature. Have a look at the data here. I'm getting the heat of combustion of a dried biscuit. I've got 2.63 grams of the biscuit, okay, 3 sig figs. XX oxygen, bomb calorimeter, calibration factor 2390. You're allowed to assume that's 4 sig figs. The temperature rose from 23.76 to 24.63. Now, both of those bits of data had 4 sig figs. But my energy released is going to be the calibration factor times the delta T. And my delta T involves a subtraction. And when I do my subtraction, and I subtract those 2 4 sig figure numbers, I get 0.87. It's accurate to the second decimal place, and it's down to 2 sig figs. 0.87 is only 2 sig figs. So when I multiply that by the 2390, my answer is only accurate to 2 sig figs, multiplication rule. And that means my final answer is going to have to be rounded off to 2 sig figs. Now, most students would give that to 3 sig figs. Now, would they check that? They might. You wouldn't take the risk. Is the logic there clear? Yep. Do you understand that? Most students would get that wrong if that was the one that was checked for sig figs. How often is that going to arise? Not very often. I can't think of many other calculations where there'll be a subtraction in the middle of the calculation. So normally, if there's nothing but multiplication and division, you can just look at your data, say, oh, the least number of sig figs is 3, final answer 3 sig figs. And that'll get you through 9 times out of 10. 2 years ago, there used to be a type of titration called a back titration. That involved a subtraction halfway through, but they've been taken off the syllabus. So the only place I'm really expecting that it might come up, and it could be where they check sig figs, would be in one of these calorimeter ones where you've got a delta T. And it turns out that the delta T has less sig figs than your original temperature data. Does that make sense? You've got a subtraction, so take that into account. Now, is that enough on sig figs? I mean, it's just an annoying mark to lose, and so many students lose it, even when it's easy. They just forget. Drill yourself. I've just done a calculation. I will check sig figs. Okay, let's get stuck into the main theory. You either like organic or you don't. If you like organic, you're probably a bit twisted. But if you do lots of organic at university, you'll definitely get twisted. Organic labs stink. Organic chemicals are smelly, often carcinogenic. I stayed as far away from organic labs as I could, but I don't mind the theory. So let's just start off. Shut me up for 1 minute. Do D. I haven't got time to spend too long. I've got too many slides to let you do too much, but try D. Handy hint, I bet you can't give the name just looking at a semi-structural formula. You'll need to write it out in full to get the name. You can look good. I'm not picking on you, you don't have to. You can just come for the colour and movement, or the occasional song. If you think you've got that, you can work your way back up the list. I'll just give everyone a chance to finish. I've chosen D because it's got a surprising kick in it. Who's got a number in their name? Who hasn't got a number in their name? The name doesn't actually need any numbers. It's dimethylpropanamine. So why doesn't it need a number for the methyls, and why doesn't it need a number for the amino group? And the answer is a 3-carbon chain with methyl groups has to have the methyls on the middle carbon, doesn't it? Otherwise they would be part of the longest chain. So it's dimethyl because there's 2 methyl groups. They're coming off the middle carbon. They have to, otherwise they wouldn't be methyl groups. So you don't need numbers to say where the 2 methyl groups are, so it's dimethyl. And given that the 2 methyl groups are taking up both positions on that middle carbon, there's only one place the amino group could go. It has to go on the end. And if it goes on the end, and it can't go on 2, then you don't need a number to say where it is. So technically, systematic naming says you only use numbers if you need numbers. With alcohol groups, I suspect VCAR would let you get away with 2,2-dimethyl. I would suspect they will even allow you to get away with 2,2-dimethyl propan-1-amine, which I bet would be a common answer. But they don't have to. Right? Technically, if you don't need numbers, you don't use numbers, and that especially arises with carboxylic acids. You see, at least twice in the last 10 or 15 years, they've asked for the systematic name of butanoic acid. They've had a 4-carbon carboxylic acid, or it might even have been propanoic acid. And any student who wrote 1 butanoic acid was marked wrong. Now, I would have said that wasn't a hanging offence. 1 butanoic acid is a name that gives you the structure, doesn't it? But you don't need the 1 because a carboxyl group has to be on the end, therefore you don't have to specify where it is. And that's been penalised. Even harsher, ethanol is a common name, but when they asked for that common name for one simple mark, a few students wrote ethan-1-ol because their teacher had said, oh, always put in a number just to play safe. Well, ethan-1-ol was marked wrong. Students should know it's called ethanol. Doesn't need a 1 and nobody would call it 1-ethanol or ethan-1-ol. Do you get that logic? I again still think that's a bit harsh. To me, the point of a systematic name is it unambiguously gives you the structure. But that's two situations where unnecessary numbers have been penalised. More commonly is that B one. Now, a quagga wouldn't do it, of course, but I've got a dibromoheptane there, and if both the bromos are on the third carbon from the right, and I would start from the right, because anyone who called it 5,5-dibromo would be starting from the wrong end. But there would be lots of students who would just say, oh, it's dibromo, they're both on 3, just call it 3-dibromo. And that would seem perfectly logical to any logical student, but it's not the systematic name. Dibromo, you have to say where it is, you have to have a number for each bromo, so it's 3,3. And just get the rule, if you're not familiar with it already, numbers are separated with commas, and numbers are separated from words with hyphens. Lots of students don't get that right.
How come it's dimethyl?
Dimethyl? If you draw the structure in full, all right, I'll draw the structure in full for you. I've got a bit of blank space here. It's 3 lots of, you're talking about D?
Yeah.
Yes? So it's 3 lots of methyls attached to a carbon. So if I draw a carbon and I put 3 methyls, CH3, H3C, note how I'm putting H's on the outside. There's my C, CH3 thrice, then there's a CH2. Oops. C, CH2. And then the NH2. You happy with that as the full structure? Can you see 1, 2, 3 carbons in the longest chain? So it's a propane chain. It's a propanamine. And then there's 1, 2 methyls coming off the middle carbon. Dimethyl?
Yeah.
Yep. And what else did we have? Yeah, so I think that third one was just another example of a semi-structural formula that probably would need to be written out in full to be sure you got it right. Last year they introduced stereoisomers, so you've got to assume that they'll be doing something on cis and trans, probably in multiple choice, but it could come up in section B. And I'm assuming that you can probably recognise a cis situation when you see one, a trans situation when you see one, and a couple of situations that might have been cis or trans but aren't, because you could flip the molecule over, whereas you can't do that with cis and trans. And then optical isomers were new last year. So I don't know what happened to my pair of enantiomers. But there's a fairly obvious example of a molecule that's got a chiral centre. It's got a mirror image, but you can't superimpose. And that's the word we would use, superimpose, but for some reason chemists think non-superposable is an acceptable word. Interestingly, I've got another example there. It's a little bit on the outer, but there's a molecule that's got 2 clear chiral centres, but is actually achiral because of that plane of symmetry. But that's possibly a little obscure. Have I got time to get you to do this? Probably not, but just have a quick go at number 2. What name would you give number 2? And don't go assuming anything's been chopped off. It hasn't. I forgot to mention, you don't have to desperately scribble down any answers on the slides there at the back of your booklet. But by the same token, don't cheat, just because the answer is in the back. Unfortunately, the VCAR examiners don't give you the answers at the back of the exam. Bastards. All right, so having a look at this one, the obvious mistake you might do is what a lot of students do, just automatically number from the left. All right, you've always got to check, should I be numbering from the left or should I be numbering from the right? If you've automatically numbered from the left, you haven't taken into account the most important functional group in this molecule is the double bond, isn't it? And you always number from the end that will give you your smallest number for the most important functional group. All right, so in this case, if I numbered from the left, I would have a 3 to tell me where the double bond was, but if I number from the right, I would only need a 2 to tell me where the double bond is, so I number from the right. And that means my iodo is on carbon 4, and a methyl group is on carbon 3, and it's in the trans position, so it's trans 4 iodo 3 methyl pent 2ene. Note hyphens separating numbers from words. Every time you've got a number, must be separated from words with a hyphen, and if you had more than one number together, they would be separated with commas. Check the other ones, but just going quickly back, this probably wouldn't happen to Kwongers, but it can. If you've used your reading time and you know, gee, this is going to be hard to finish in 2.5 hours, it seems pretty long. You don't want to get to the end of the exam and find you haven't been able to do the last couple of questions, because very often they don't grade the questions very well, and sometimes the last couple of questions have easy marks. So what you don't want to happen is to get bogged down in multiple choice. They're 1 mark each. You can't afford to spend 5 or 6 minutes for a 1 mark question. And if that's happening, and it happens for 2 or 3 multiple choice, what will happen? Your panic will start rising, won't it? That is the absolute worst thing that can happen in an exam. In an exam, you've got to treat it as a game. It's a game between you and VCAR, and you're trying to suck as many marks out of the bastards as you can. That's just the game. It's like an Easter egg hunt. That's a bit Christian, isn't it? Never mind. We've all gone hunting for things in the garden. Some of the eggs are easy to find, some are harder to find. But you try and find as many as possible. So treat an exam the same way. You grab all the easy marks and you try to grab as many of the harder ones as possible, but you at least attempt everything and try to get as many marks as possible. And that's all it is, a cynical exercise at getting as many marks as possible. You can't afford not to finish. So you can't afford to bog down, and sometimes in multiple choice, realistically, you know you've got a 1 in 4 chance of guessing. And sometimes if you can eliminate 1 or 2, you can get the 1 in 2 chance of guessing. Well, sometimes the odds are on your favour. Guess and run is sometimes a very good strategy, but always mark it with an asterisk. I'll come back and check this again. You have to do it in pencil anyway on the mark sheet, so you can always rub it out and change your mind, but never change a guess unless you've got a good reason to. You'd be surprised how often your first guess was intuitive, something in your subconscious gave you the right answer. So don't just change a guess just because you think, oh, well, I've chosen C, but I've got too many C's, I'll change it to guessing B. Very often your first guess is your best guess. But I would say here's a couple of situations where that might arise. I reckon certainly in 4, to be sure you had 4 right, you would have to draw out all the isomers, wouldn't you? Yep. And that's going to be time consuming. And you might miss one anyway. So you might spend all that time and still get it wrong. Sometimes you could say, well, there's bound to be more than 2. That's down to a 1 in 3. I reckon there's probably more than 3. So it's either C or D. 5's a bit too many. You might guess 4 and you'd be lucky. Right? But some people would be lucky for the wrong reason. It is 4. And some people would say, oh, there's 4 carbons. There's 1 chloro. 1 chloro, 2 chloro, 3 chloro, 4 chloro. Wrong logic, but they'd get it right for the wrong reason, yeah, which is really annoying in multiple choice if you're a teacher.
For the systematic name of the second molecule,
yep.
Why is it trans and not cis?
Why isn't it trans?
Why is it trans and not cis?
The 2 major things, you've got a CH3 down the end, so you've got to take that into account. And then the major group is the one with the I, and that's in the trans position, isn't it?
But two methyl groups on each carbon are the same size as the double bond.
So, trans is based on the longest thing, and the bit that's longest is the bit with the I in it. And the CH3 on the other side of the double bond is in a trans position. The fact that they're both methyls is irrelevant. H is totally irrelevant because that's the smallest thing. So it's a choice between the H and the CH3. There's a CH3 on the right. Yep, CH3 on the right. Sorry, I wish this pointer was working, but it's not. Then you've got the CH3. Yes, that is in the cis position, but this thing is much more significant than that. So that's the significant thing, more significant than that, and it's in a trans position with this CH3. And that's how you base the trans.
So it's not related to...
It's not related to whether they're the same. Definitely not related to identical things. You hadn't picked that up?
No, not at all.
No, that is definitely the rule for cis and trans. You certainly don't, because there often won't be identical things.
So there doesn't have to be two hydrogens on
No, no. You could have. I could have had. If this had been CH3 CH2, and that had been CH3, that still would have been trans. Question?
So if the methyl group, like the CH3, was up the top instead of the CH, so if they swap positions...
Yes, on the right-hand side,
Yeah,
that would be cis.
Yeah.
That would be cis.
Because they're two longest.
Yes, yes. Yeah, that's a good answer to that question. If that CH3 had been up there and that H had been there, that still would have been trans. Oh, sorry, no, that would have been cis. Yes, sorry, my mistake. Yeah. By your logic, because by your logic it would have been trans. Yeah. No, it would have been cis. If that CH3 was up there, damn it, why isn't this bloody mouse working? No, it's gone. Maybe if I escape. Come back in. There, we've got it. Okay. Just to clarify, there's a... No, there it is. The CH3 here is in a trans position to this major group here. This group here is more important than that group there. So this major group here is in a trans position to that CH3. If I took this CH3 and moved it to here and put this H down there, then it would be in a cis position to that major group. And you would not call it trans just because the methyl was trans to that methyl. That's not how it works. Okay? So if 3 would have been annoying, you'd have had to sketch out the structures just to check where the chiral positions were, but that's probably not too time consuming, so it's probably worth spending the minute or so that it's going to take you to do that. But the C4H9Cl is definitely off an old question, and that's annoying. You've really got to sketch them out, and it turns out there's 1 chloro, 2 chloro, not 3 chloro, that would be the same as 2, not 4 chloro, that's the same as 1, but there'll be a couple of methyl propanes as well, and they will need numbers. Okay, into the exciting reaction types. Exciting if you love organic chemistry, not so exciting if you don't love organic chemistry, but promise yourself you will know it and be really familiar with it all the way through till November the 13th. You will then wipe your brain. But there is stuff you will definitely need to know on November the 13th. So substitution reactions is one of them. And there's a major beware, but let's just see this one I've stolen from Chemistry 2. I don't know why they started with the functional group on the right-hand side and then turned it around and put it on the left-hand side. Maybe they're trying to illustrate this idea, HO, not O, on the left-hand side. Reasoning being, if you'd written OH, and that's going to be quite common, that might look okay until you do it as a full structure. As a full structure, you definitely can't do that. Would you agree? You can't have an H between two other atoms. H can't form two covalent bonds. So that would be marked wrong. The VCAR logic would be, nope, that could be misinterpreted. That would be marked wrong as well. So if you've got an OH on the left-hand side, write it as a HO. HO, not O, on the left-hand side. Now that most recently came up when they gave you a disaccharide and asked you to draw the structure of the monosaccharide. And of course with glucose you've got a whole lot of OHs all around the molecule, and every student who put an OH on the left-hand side lost the mark, because it was deemed as being an H between an O and a carbon. So if you just have that little rule, if I've got a hydroxyl group on the left-hand side of the molecule, write HO. And if you're really fussy about that, if it's an amino group, I'd write H2N. And if you're really, really fussy, if it's a methyl group, I'd even write H3C, just to make sure there's no chance of them misinterpreting that you think there could be an H between one atom and another atom, because an H can't form two covalent bonds. Alrighty, so turn them around. Now, the critical thing about substitution reactions from an industrial chemist point of view is the feedstock for nearly all organic chemicals comes from crude oil. And crude oil, of course, is alkanes. Now, because we're used to seeing alkanes end up in our cars, and they burn very well, and they can be quite explosive, a lot of people think alkanes are really reactive. Well, with oxygen, they are. Alkanes love oxygen, and they'll burn quite happily in oxygen, but they don't produce useful products. They produce carbon dioxide and water, and that's not terribly useful, especially when they disappear into the atmosphere and contribute to global warming. But if we're going to use alkanes as our feedstock, then we need to change them into something else, and it's actually very difficult. After all, they've been sitting for millions of years away from oxygen and just not reacting with anything around them, because alkanes are actually very unreactive. So there's not many things other than oxygen that actually do react with alkanes. So this substitution idea, start reacting alkanes with chlorine, that's your key knowledge, that alkanes will, under the right conditions, react with chlorine. But just remember, you always get an annoying mixture of all the possible chloroalkanes. If you want just one of the chloroalkanes, you'll have to separate it from all the other ones. And 2 years ago, you would have had to know the principles of the technique they use, which is called fractional distillation. I still think you need to know the name, that if you get a mixture of chemicals, as you will, a whole lot of chloroalkanes, then you'll have to separate the one out, or the ones you want, by fractional distillation. So that's there down the bottom. Getting into really sexy territory, and you're all adolescents, your ears perk up when I say that, but when I say sexy, I don't mean anything to do with sex, I just mean this is something examiners love testing. It's sexy. Question? No. No, very little to know. Just going back there, you need to know, well, we'll get to the summary at the end, but definitely what's the significance of it? Why is it even in the course? Because it's the starting point for crude oil to be turned into other chemicals. It's fairly easy to substitute the chloro group once you've got a chloro group on the alkane. Yeah, so that's the significance of it industrially. But here, this is much more interesting reaction. Addition reactions, definitely sexy, and the sexiest one is adding water. Now water, the adding molecule splits in two. Now you can't split it in half, so it has to split into an OH and an H. One bit goes to one side, the other bit goes to the other side. In this case, it doesn't matter where they go. You could turn that molecule around if you put the OH on the left. However, in 2013, they decided that adding water to a non-symmetrical alkene was going to be one step too far. Because how many of your teachers have told you about Markovnikov's rule? Did anyone get a mention of Markovnikov's rule? Now, I think lots of teachers don't even know it. You'll hit it in first year university, and it tells you that when you have an addition reaction, a hydrogen, if there's a choice between where a hydrogen goes, it always goes to the carbon that's got the most hydrogens. The Americans say them as has gets. We might say the rich get richer. And it tells you that if you had propene, can you just draw propene quickly? Just draw propene, carbon, double bond carbon, single bond carbon. Now, if you wanted to add water to that, you'll see it on lots of practice exams, and they're wrong. They will want the OH to end up on the end carbon. They'll want the OH to add to the end carbon, and they'll want the H to go to the middle carbon. In reality, something like 90 to 95% of the OHs will actually go to the middle carbon, and you'll get the 2-propanol, not the 1-propanol that most of the practice exams assume you'll get. That's Markovnikov's rule. It's not in the study design. But it means you do get a mixture of the possible isomers, the 2 alcohol isomers, and most of them will be the 2-ol, with the OH coming off the middle carbon, because the H from the H2O will go to the end carbon. The carbon that's got the most hydrogens picks up the hydrogen, is Markovnikov's rule. Now, that's not been mentioned. It's not in the syllabus. So what VCAR did in 2013, I'll come to you in a second, is they said, we will only ask you to add a non-symmetrical molecule, like water, to a symmetrical alkene. Ethene is symmetrical. 2-butene is symmetrical. If you can picture in your mind what would happen if you added H2O to 2-butene, you would get the OH on one of the middle 2 carbons, and it wouldn't matter which one. But if you had 1-butene, Markovnikov's rule would kick in, and you'd get 2-butanol in preference to 1-butanol. You get a little bit of 1-butanol, and you could separate it out by fractional distillation, but Markovnikov's rule would say the H would go to the end and the OH would go to the inside. Now, that's not syllabus material, so it shouldn't be on a VCAR exam, but it's on a hell of a lot of the commercial practice exams, and they're just plain wrong. They're just wrong. Now, your question?
Just a question about addition reactions.
Yes.
How do you word and we classify it as a hydrolysis reaction?
No, you wouldn't. Can be called hydration. If they ask for a name, call it addition. It's actually not technically hydrolysis. If you look up your glossary at the end of Chemistry 2, it'll tell you that hydrolysis is a slightly different thing, and it's not just the addition bit. There's a bit more to it, to a hydrolysis reaction. So don't use the word hydrolysis there. Look, you might get away with it, but technically it's called hydration if you had to bring the water into it. Now, what else is sexy about this equation? Well, it produces ethanol, so that's a really common exam question. You don't go near an exam without knowing how to add water to ethene, because it produces that mind-altering, performance-impairing recreational drug called ethanol. And you are all about to or have turned 18, so you're going to be exposed to this evil drug. We'll talk more about that at the end if I get time. So, sexy reaction. Very often on exams, what do you need to know? Probably not the temperature, although it's above 100. That's critical, because it's not water liquid. That might be significant. If you bubble ethene into water, I can tell you exactly what will happen. It'll bubble straight out again. It's a non-polar molecule. Water is a polar solvent. It will not dissolve in the water, won't get a chance to react at that low temperature. It'll just come straight out. You will not get a reaction between ethene and liquid water. So it certainly has to be in the gaseous state, and it needs a catalyst. Now, do you need to memorise the catalyst? It's never been required, but it just might be. I think there are 2 catalysts you should waste a couple of neurons on. That's probably one of them, but that's it. End of story. The syllabus does not expect you to memorise a whole lot of different catalysts for different reactions, but I'd commit the acid catalyst, the H3PO4, for this one because it's such a sexy reaction and it just completes it. All right, but H2O gas, now you wouldn't normally put symbols of state on a structural formula, and I would suggest that an addition reaction should be done with structural formulae. It makes it much more obvious where everything's going, rather than trying to do it with molecular formulae, and everything would be in the gas state for that reaction. Next sexy reaction is condensation. And the definition of this is wrong in Chemistry 2. I'm trying to get them to fix it. Let's go back to addition. In an addition reaction, the 2 reactants join and you get one product that is the sum of the 2 reactants. That's why it's called addition. The product is the sum of the reactants. In a condensation reaction, The product, the main product, is smaller than the sum because a small molecule gets flipped out. The product is smaller than the sum because a small molecule is eliminated. That's the condensation. In the same context as a condensed book. Maybe you've never heard of condensed books, but some poor authors have their lovely novels condensed. Whole lot of words taken out just so they're quicker to read. You know, the guts of the story's still there, but they've taken out half the words to make it a condensed book. It's condensed in that sense. Something's been taken out and you've still got the guts of the reaction. So it's not condensation because water is a product, because water doesn't have to be a product. There are plenty of condensation reactions where other small molecules are released. HCl is a typical small molecule that's often released in condensation reactions. So it's not condensation because of the water, even though in pretty much every condensation reaction you'll see, water is the small molecule flipped out. Am I making sense? But the water isn't part of the definition of why it's called condensation. And if you've picked up that idea, then that's an incorrect idea. Right? The product is smaller than the sum of the reactants because a small molecule, often water, has been flipped out. So it's been condensed a bit. There used to be only one sexy one, and that was the carboxylic acid reacting with the alcohol to make the ester. We'll see that on the next slide. It's called esterification. But last year they adding an amine to a carboxylic acid, so you've got to regard that as almost equally sexy because it's new. So if they're doing a reaction pathway, it used to be fairly predictable it was probably going to end up in an ester, but now it's possibly only equally predictable that it might be an ester or it might be an amide. You've got to watch out for both of them. So the esterification used to be the only major condensation reaction, and the major beware there was this is the other catalyst that you need to know. That has been tested more than once. What is the catalyst that makes the carboxylic acid react with the alcohol? And it's concentrated sulfuric acid. Why? Because concentrated sulfuric acid also acts as a dehydrating agent. And if your teacher hasn't demonstrated adding concentrated sulfuric acid to sugar, hands up if he, she has. Oh, come on. It is the most fun demonstration. It's pornographic. Absolutely appeals to teenagers. You add beautiful crystalline white sugar, yeah? Pour on some sulfuric acid, and although there's no actual water in the sugar, the acid behaves as if there is and sucks all the H2O out and generates a lot of heat while it does it, and the beautiful white sugar becomes a column of carbon which slowly rises out of the beaker. This black, dirty great column. If you get the right, 100 ml beaker works beautifully. Right? And the girls always ask, can I touch it? And I always say no. So if your teacher hasn't demonstrated concentrated it used to be really relevant when you used to have to study sulfuric acid in detail, the dehydrating property, but it's kind of still relevant here. Get them to get him or her to demonstrate the dehydrating property of concentrated sulfuric acid by adding it to sugar. But it's an equilibrium example here. If you remove the water as it's produced, by it acting as a dehydrating agent, then it's going to favour the forward reaction, isn't it? And therefore, that's an equilibrium, because the next slide will say, and yes, we have to now know the reverse. Take an ester and put the water back in. Hydrolysis. Now, that is hydrolysis. You might want to check the difference between the water there as a reactant and the water in the addition reaction, which wasn't technically hydrolysis. And hydrolysis comes up again in food digestion. So we've added that to our list of name types that you might have to know about. But the beware here is so many students give too much information. If they ask for the catalyst, you'll get away with H2SO4. You'll get away with concentrated H2SO4. You'll get away with H2SO4 liquid. All of those three would be acceptable. But H2SO4 aqueous has always been penalised because it doesn't work. And you should be able to figure out why it doesn't work. After all, if it's a dehydrating agent, what's the point of H2O, H2SO4 aqueous, which has already got a whole lot of water in there? Yep, so that's why it was penalised. It has to be not dilute, so aqueous was always penalised, which is pretty mean. It means you've added more than you needed. If you just had H2SO4, it would have been marked right, because that would have been read as pure H2SO4. But putting H2SO4 aqueous, you automatically lost the mark. That's mean, but it happens. Okay, so the hydrolysis, because if you've learnt the forward, it's easy to get it going backwards again. Definitely sexy, the oxidation of the alcohols, and they've added more than what they was. In 2016, you only had to know about primary alcohols being oxidised. Now you have to know about secondary alcohols and what happens to a tertiary alcohol as well, which of course is nothing. It's much more difficult to oxidise a tertiary. Why? Well, you probably don't need to know, but with a primary alcohol, the OH is on the end of the chain, so it's easy enough to replace that with a COOH, and that's definitely oxidation because it's gained oxygen, if nothing else. But with a secondary, you can't turn this middle carbon into a COOH because then you'd have too many bonds on the carbon. So you can't get the carboxyl forming on that middle carbon, so you end up with a ketone instead. Now, you don't have to name ketones, that's not been added to the syllabus, but you definitely need to recognise a ketone when you see one, and you definitely need to be able to recognise spectra. Ketones often give you very nice NMR spectra, so they're quite likely topics for spectroscopy, even though you won't be asked to name the molecule. That's not syllabus material, but you probably should know it anyway. A 3-carbon ketone would be called propanone, although you might see that called dimethyl ketone in an old name. The middle stage of the oxidation, this definitely is still sexy, probably not required, it's not in the study design, but it would be worth registering that. Some of the practice exams I've seen have required you to know that you get an aldehyde as an intermediate step between the primary alcohol and the carboxylic acid. All right, so lock that in. And then if you've got a photographic memory, you definitely take a screenshot of that. So you can just picture, hey, my question is starting here and it wants to end up where? Well, how do I get from A to B? Why is this regarded as so important? I think it's the organic chemists somehow getting on the committee for setting your design, because this is what just gives organic chemists, they just go bananas. They just love to work out how many different ways they can get from A to B. And maybe that's why they brought in atom economy last year, because that tells you how efficient you're getting from A to B, doesn't it? So let's just imagine that we wanted to go from ethene to ethanoic acid. This little flowchart would say, well, the obvious way is to do the addition reaction with water. Well, H2O gas anyway. Steam, turn it into ethanol and then oxidise it. But an organic chemist would say, oh, but what if I didn't have any water? What if I had some HCl instead? I could take it via the chloroethane and then do a substitution. Or I could be even really, really stupid and go back to my ultimate definition of saturated, unsaturated. Where did those two stupid terms come from? And they came from the fact that if you've got a carbon-carbon double bond, it hasn't got as many hydrogens as it could have. You could add more hydrogen to that molecule and saturate it with hydrogen. So ethene is unsaturated with respect to hydrogen, but ethane is now saturated. So that's where the terms came from, and it's now been extended to any reaction of a molecule that's got a carbon-carbon double bond. But you've got to be very careful. If they say, how do you define unsaturated, do not say, oh, it's a molecule with a double bond. Because 50% of the state will. A molecule with a double bond. Carbon-oxygen double bond? No. Carboxylic acids have a carbon-oxygen double bond, but they're not unsaturated. So you've got to be very specific. It's got to be a carbon-carbon double bond or a carbon-carbon triple bond. Either of those two are unsaturated. Historically, you could add more hydrogen to them. So an organic chemist would say, let's go the historical route. Let's turn the ethene into ethane, then substitute it with chlorine, then substitute it again, and in a long roundabout way we'll have got to the ethanol. Wow, wasn't that fun? And a logical person would say, no, what a stupid waste of time. But don't try telling an organic chemist that. So an exam question would want you to go the more logical way, but might in an atom economy type sense ask you to work out, well, what would be the atom economy of going a dumb way? Because green chemistry would say you always go the most sensible way that probably has the highest atom economy. We'll get to that. All right, so the logical starting points is alkane or alkene, and the logical finishing point of a reaction pathway is probably now either an amide or an ester. It used to be predictably an ester, now it's not so predictable, it might be an amide. So your typical one is on the next slide, but I haven't got time to let you have a try at that. So maybe you take that home. We'll just quickly say, well, if I want to make ethyl propanoate, plan it out. My last precursors will have to be ethanol and propanoic acid. What am I starting with? Propane. Okay, so I've got to know how to turn propane into propanoic acid. And what am I starting with? Ethene. So I've got to know how to turn ethene into ethanol. All right, well, that's the easy bit. So on my quick answer, which is up the back, don't go cheating, just try this for yourself. Ethene plus gaseous water could be turned into ethanol. There's one thing I need. And then my propene would have to be chlorinated. I'm going to get an irritating mixture of chloropropanes, which I'll have to get the 1-chloropropane from by fractional distillation. I'll then substitute again to get the 1-propanol, because I need 1-propanol to oxidise to propanoic acid. But if you've got your pathway memorised, then that's clear. Your propene would go to 1-propanol, would go to propanoic acid. Your the other way around. That was ethene going to ethanol, and propane was going to 1-chloropropane, was going to 1-propanol, was going to propanoic acid. Join them together to make the ester. Now again, some students love that. Well, I'm sorry, they're the A+ students, because this is often 4 or 5 marks, and the students who just know how to do these just lap it up. So if you want to join them, you'll just know how to do it. Yep, that's just too predictable a question not to go in, not being pretty familiar with that sort of reaction pathway possibilities. Where are you starting with? What are you trying to finish up with? Okay, so one quick slide on atom economy, but only mainly because the data book has got the formula wrong. Has your teacher pointed that out? The formula in the data book is an oversimplification. It just says add up the molar masses of your reactants. No, you've got to take the stoichiometry into account, such as this example that I've stolen from Chemistry 2. In the atom economy for reaction 1, we have to double the molar mass of the ethene, double the molar mass of the chlorine, and add the molar mass of the calcium hydroxide, because that then gives me the sum of all the atoms that are in the reactants. And then I've got to double the molar mass of the ethylene oxide to put that over, so I get 88 over the sum of all those other molar masses. Now, if you were just literally reading the formula in the data book, you would not be doing that, because it doesn't tell you to do that. It doesn't tell you to take the stoichiometry into account. Have you encountered that before? Well, just check the formula in the data book. It doesn't tell you take the stoichiometry into account. Whereas if we go reaction 2, you could get this wrong. Yes, we've only got one product, so that's not going to be a problem. I've got 44. But my reactants have got ethene and half an O2. So I add the molar mass of the ethene to half the molar mass of the oxygen. Now, all the data book tells you to do is add the molar masses of your reactants. Can you see that that's not quite right? Have I won you on that one? I don't know what VCA are going to do about it, but I know there are a few teachers that are pretty annoyed that there's something wrong in the data book. And I don't know if you noticed this year, they've changed the data book twice because they stuffed up the structure of lactose. Twice. Unbelievable. Never mind, we can't criticise VCA too much. I'm sure they're overworked and underpaid, like most teachers. All right, why do we need any bonding? There is no topic in Year 12 that covers bonding. But there are still going to be bonding questions, and VCA expects you to remember everything you learnt about bonding in Year 11. Well, actually, not quite everything. because not much bonding is relevant that isn't to do with molecules. It's all to do with the organic chemicals, and most of them are molecules. But I will just point out, you've been doing this since year 8 probably. You first got the models for solid, liquid and gas, so you've got these sort of clear pictures of little circles starting to move and then separating and ordered structure and all that sort of thing. But what you might not have picked up, and which I think is reasonably significant, is lots of students will say, when you go from the solid state to the liquid state, the forces between the particles get weaker. How many people think that is a true statement? When you go from solid state to liquid state, the forces between the particles get weaker. I see my students write that all the time. If you do physics, you'll know that's rubbish. Because electrostatic force, don't have to know this for chemistry, but gee, it helps, is some constant, Q1, Q2, they're the two charges that are attracting or repelling each other, and then there's a d squared on the bottom line. All right? Now, when you've got these particles, well, whatever charge they've got, there's a certain amount of charge, Q1 and Q2, that's attracting each other in the solid, yep? And then there's not much distance between them. When you go to the liquid state, have you done anything to the charges? No, you haven't. Whatever charges you had in the solid state, you've got exactly the same charges in the liquid state. Have you done anything significant to the distance between the particles? Well, sometimes there's a little bit more jostle room, but sometimes there isn't. If you think about ice going to liquid water, ice is actually less dense than liquid water. So the particles actually get closer to each other. So if you look at that formula, when ice melts, the D gets a little bit smaller. The Q's are the same. The electrostatic forces are actually stronger. Don't tell me they've got weaker when ice melts. They've actually got a little bit stronger. So why has it melted? It's not because the forces got weaker, it's because the particles got more energy, and they had enough energy to overcome the forces. But the forces haven't become significantly weaker, and sometimes they get stronger if the distance between the particles actually decreases. Now, water's actually a bit weird. Not many substances do that, and normally when you melt something, the particles do get a little bit further apart just so they can move relative to each other, but not in water. And that's the structure of, that's to do with hydrogen bonding, only allowing each water to have 4 nearest neighbours and lots of empty space, which they don't need when they melt. On the other hand, you can say, looking at the model, when I boil a liquid, the forces do get weaker because the particles will be, on average, much further apart. The D will be much bigger. Inverse square law, the bigger the distance, the weaker the force. So having just quickly reviewed that, whoops, wrong way. You probably had something like this in year 11. Hopefully you reviewed it again this year because you might still need it. Metallic bonding, no, throw that out of the window. I can't think of anywhere that's relevant. Ionic bonding, probably not very relevant, but ions just might come into ion dipole attractions, just might still be relevant, but most bonding will be to do with molecules. Probably don't need covalent lattice structures anymore in year 12. So focus on everything you ever learnt about molecules, and remember the easy molecules are the ones that are non-polar. So you've got to be able to pick between whether a molecule is polar or non-polar. Make sure you've reviewed that. I've sort of summarised maybe how you do that. The simple rule is if you can't see that it's definitely non-polar, then it probably is polar if you've got unequally shared electrons. So if you've got 2 different elements in a molecule, chances are it's polar until you can prove otherwise. Default position should be it's probably polar. So sometimes you've got symmetry that cancels out the polarity and you end up non-polar. Pray for that, because then the only forces that you have to worry about are dispersion forces. If it's polar, and lots of them will be, then you've got to worry about dispersion and dipolar. And never ignore the dispersion. They're often stronger than the dipolar forces, or the dipole-dipole attractions, whatever you want to call them. And then it goes one step further, and this is really sexy. Are the dipolar forces, the dipole-dipole attractions, the sexy type known as hydrogen bonds? It's not a different type of bonding. It's a special case of dipole-dipole. Better review that. So because it's so sexy, be absolutely clear it's a dipole-dipole attraction where the delta plus is on an H, and it's a significant delta plus because it's bonded to one of the big three electronegative elements, F or O or N. The delta minus has to be on one of the big three, F or O or N, and it has to be a significant delta minus because it's bonded to something much less electronegative, preferably hydrogen, but could be carbon. The biologists want carbon, so that they can have a CO bond having a significant enough delta minus. Now, why is that so super duper attractive? It's because if you think about it, in this molecule, that delta plus is on an H, and the H only has one electron, and that electron is in this covalent bond here, isn't it? Unlike any other element that might have a delta plus, it won't have any electrons here. Do you agree? The hydrogen will not have any electrons here. Any other element will have electrons there. And any other element, the electrons here will stop this molecule getting too close to this delta minus. But hydrogen doesn't have an electron there, so the hydrogen with the delta plus can get pretty damn close to that delta minus. The D squared kicks in, and that much shorter distance allows the bond to be much stronger. Is that making sense? So that's why the dipole-dipole attraction that goes with hydrogen bonding is much more significant than any other dipole-dipole attraction, which is often really quite insignificant compared to the dispersion forces.
If you say you had two carboxylic acids and you were observing the bonding between one of the hydroxyls and another C double bond to an O.
Yeah, that would count as hydrogen bonding. Yep.
So they don't necessarily have to.
Yep, because you'd have a delta plus on an H, which was bonded to an O, and you'd have a delta minus on an O, which was bonded to a carbon. And carbon's good enough to give that a big enough delta minus to count. I find that a bit unconvincing, but because of biology, so many situations like that happen in biology that the biologists want to call it hydrogen bonding, so we go with that one. All right, so are you going to get a straight bonding question? It's possible. I don't want to spend too long, but I'll give you a couple of minutes. Just write down a couple of points for number one. Number one is definitely still a bonding question. Should have been able to do it last year, still should be able to do it this year. Do not write an essay. Do not write a paragraph. Dot points are perfectly acceptable. It's not actually a fair comparison. I can't afford to give you too much more time. But I don't know. I know there are a lot of teachers that say you can't use dot points. That's rubbish. When you read the examiner's reports, they'll tell you, you get 1 mark for this point, you get another mark for that point, you get another mark for that point. Why not make it easy for your marker? They can just say, oh, yep, that point's worth a mark. Nope, that point's rubbish. Yep, that point's worth a mark. 2 out of 3. If they've got to wade through a dirty great long paragraph, That's hard to mark, especially when some of your writing is tiny or some of your writing is almost illegible. Use as few words as possible, but get the idea out clearly, and dot points is the clearest way I know of getting these ideas. Now, would you need to make that first dot point? Probably not. Question?
I was just going to say, some teachers have said that if it's worth 3 marks and you put 4 dot points, often they take it first, like...
No, that's not true.
They just find that...
They will find the 3 marks that they're looking for. If one dot point contradicts another dot point, then you lose the mark that you've got for that. But if it's irrelevant, it's just ignored. Nope, just ignored. Yep. All right, so this probably wouldn't be worth a mark, but G, it sets up your question. The question is about comparing boiling points. What is boiling point related to? The strength of forces between the particles. Because that then tells you, oh, I better say what the particles are, and I better say what the forces between them are. Right, so the particles in both cases are molecules, but one of them's non-polar and one of them's polar. That will be certainly in the marking scheme. The non-polar ethane will only have dispersion forces. The polar ethanol will have both dispersion and dipole-dipole attractions. But then comes the kicker. The dispersion forces will actually be stronger because it's a bigger molecule. It wasn't really a fair comparison. But the most important reason why it's higher is that the dipole-dipole attractions will be called hydrogen bonding. There'll definitely be a mark for saying that the dipole-dipole attractions are hydrogen bonds. Why? Because that's sexy. If the hydrogen bonding is relevant, always mention it. The other question is probably less relevant now, except an interesting contrast. 2 years ago, aspirin was on the syllabus. You definitely had to answer a question like this. But now, let's just treat it as a bonding question. Why would this be not very soluble in water? Because it's mostly non-polar. That benzene ring is non-polar. This CH3 down the end is non-polar. A little bit of polarity on that O, a little bit of polarity there. So they could form hydrogen bonds to water, so it'd be slightly soluble. But this guy has got charges. And as soon as you've got charges, then you can form iron dipole bonds. Q1, Q2, if it's hydrogen bonding, it's partial charge bonded to partial charge. That's not very big in terms of Q, so the force isn't very strong. Do not ever say hydrogen bonding is strong bonding. It's not. It's weak bonding. It doesn't take that much energy to boil water, and that is about as strong as hydrogen bonding gets, the hydrogen bonding between water molecules. So if you've got just hydrogen bonding, you've got partial plus, partial minus. If you've got iron dipole, you've got a chunky plus or a chunky minus that can form a bond to the delta plus or delta minus on the water, and that's got to be stronger. So an iron dipole bond is always going to be stronger than hydrogen bonding, so the sodium salt's going to be much more soluble, because that's what solubility is related to. But again, you could read the answer there. What's the crux of the question? Answer it in dot points. Don't write an essay. You'll be doing your assessor a favour, and that is actually to your advantage. Don't make them wade through. They might just give up. Yeah, make it easy to mark, and they'll just give you the credit you deserve. Oh, sounds like a song time. Since we're on bonding, a little love song. Just a little atom of chlorine, valence -1. Swimming through the sea, digging the sea, just having fun. She's not worried about the shape or size of her outside shell. It's fun to ionize, you're just a little atom of steel with an unfilled shell. Somewhere in that sea lurks handsome sodium, with enough electrons in his outside shell, plus that extra one. Somewhere in this deep blue sea, there's a negative for my extra energy. Yes, somewhere in this foam, a positive will find a home. Unsuspecting chlorine felt that electrostatic pull. She looked down and her outside shell was full. Sodium cried, what a gas be my bride, and I'll change your name from chlorine to chloride. Now the sea evaporates to make the clouds for the rain and snow, leaving a chemical compound in the absence of H2O. The crystals that wash upon the shore are happy ones. So if you never thought before, think of the love that you eat when you salt your meat. I don't even want to go near all the wrong chemistry in that, but never mind. Sodium atoms just don't meet up with chlorine atoms. It just doesn't happen in nature, but it's lovely to think of. And incidentally, if you're in Unit 3, I told you about my theory that metals are male and non-metals are female, and never mind. No other teachers seem to teach that. It seems logical to me. All right, so where does bonding fit in chromatography? I don't want to spend too long on chromatography. We're running out of time. And it's been downgraded since 2 years ago. You used to need to know a lot about chromatography. Now, I reckon, apart from the sort of basic principles, you really only need to interpret calibration graphs. And if you're given the peak area of a peak in your chromatogram, what would be the concentration? So a bit of quantitative analysis of an organic molecule that had been separated by chromatography. So hopefully you've done enough on that in class. I won't spend time on that. The mass spectrometer, technically you don't need to know how it works, other than there is such an easy mark to lose. If you don't understand that for a molecule to go through a mass spectrometer, it has to be ionised, because that's the only way to accelerate it. You need to get it accelerating into a magnetic field, and it has to have picked up a positive charge because there's a negative plate here as the first plate that's going to attract it. Then there's a positive plate on the other side that repels it. Then there's another negative plate that attracts it, and there's holes in all these plates. So your molecules get faster and faster and faster until, whee, they're really flying out the other end, and then in the magnetic field they get deflected. Now, you just have to be able to interpret the mass spectrum, but in terms of the particles appearing in the mass spectrum, they won't be there if they haven't picked up a plus charge. So many students leave out the plus, and that always costs them a mark. Does that make sense? Any molecule you say that's appearing in the mass spectrum must have a plus on it, because it wouldn't be in the spectrum if it hadn't picked up that positive charge in the Zapka-Power region. Understand what the Zapka-Power is? I'm just trying to make it a bit fun. Yeah, that's just electrical discharge, knocking an electron out. So the key thing is what we do there. There is a clear beware. Occasionally you even see it in teachers' notes. Because of this 100, you associate 100 with percent, don't you? That is not a percent. It certainly isn't a percent abundance. A little bit of thought will tell you that. This peak at 43 cannot be 100% abundant, because otherwise there wouldn't be anything else in the spectrum. So it's just a relative intensity where the most abundant peak is set, is given a value of 100, just so you can see how the relative abundance of other things. So something that was half the size of that peak would have half the abundance. Right? So it's a relative abundance would be 50, but only relative to this one being 100. It's not 50% of the molecules being there, just like that's not 100% of the molecules being there. I just mentioned that because I remember seeing that in some students' answers, that they thought this was percent abundance of these particles. But note, all the particles that have been labelled have got pluses on them. So what do you have to be able to do? Well, basically the right-hand peak you assume is the molecule coming through with a 1 plus. It may well not be the most abundant peak. Once the molecule picks up a 1 plus, it becomes very unstable and tends to fragment even further, so in an unpredictable way. So I've just said on the previous slide, here are your basic skills. You should be able to write a balanced equation for the production of the parent ion. You've got a couple of choices for that, and you should be able to write an equation for the base peak. Haven't got time to revise that now, I'm flying. All right, spectroscopy. Note the difference. VCAR got it wrong. It's in the study design. They call it mass spectroscopy. Rubbish. Spectroscopy is all about using radiation. There is no radiation involved in mass spectrometry. Question?
What was that phrase? Do we just show that
Yes, I was hoping someone wouldn't answer that because I've forgotten to do a slide with an illustration. You have two choices. Since you've brought it up, we'd better cover. I've got some spare space here. If we have our molecule, I don't know, let's take a really simple molecule like CH3, CH2OH. You have two choices. I know the book likes doing this. Plus an electron going to CH3, CH2OH. I'll just do the parent ion first. And then to balance that, a plus, and then to balance that, you've got to have two electrons. That is so dumb, isn't it? Mathematically, cancel one of the bloody electrons and just have that. So either of them would be accepted. That first one was in the book, but that's got to be acceptable, doesn't it? Because it's just mathematical sensible. All right, now I've got this. Now I want to fragment that. CH3, CH2, OH plus will fragment. Now it'll fragment into another positive charge. Let's whip a CH3 off it and say it becomes CH2OH plus. Now you don't have to know where the plus is, so a safe thing is just put a square bracket around it. Just like I could have had a square bracket around that. I don't know where the plus is on the molecule, and I don't have to know, but there is a plus somewhere on the molecule ion. And so there's that. Now, your question was, what's the other bit? Well, I've taken off a CH3, and it will have an unpaired electron. Now, it's never been tested, but the unpaired electron will be on that carbon, and so it's a radical with an unpaired electron. So I think it makes you look intelligent if you do that. So that would be my recommendation. Yeah, just put an unpaired electron on the radical. But I don't think the syllabus requires you to know that it's called a radical. It's not mentioned in the study design. It is in your textbook, and that should be enough if you had to write an equation. Yep, sorry, I've got to put a slide. I've got too many slides, that's what I was trying to avoid doing that. All right, so we're clear. That was spectrometry, did not involve electromagnetic radiation. Spectroscopy does involve electromagnetic radiation. There is a difference. Last year you would have looked at AAS and UV Vis. They used to be on the Year 12 course. They got put into Year 11. There shouldn't be anything on AAS and UV Vis, but they might still expect you to remember that. So just be aware in both AAS and UV Vis, the radiation is causing electrons to go from lower energy levels to higher. That would be absorption, or from higher to lower, that would be emission, but that was last year. But it's to do with electrons jumping between energy levels. On the other hand, let's get very clear. NMR is about radio waves, low energy radio waves being absorbed. Now, what are they doing? It's quantum mechanics. You shouldn't have to know. What the hell is the spin state of a nucleon, a particle in the nucleus? Yep, you have very hazy understanding of that, am I right? Because you haven't done any quantum mechanics. So, to me, explaining why you get NMR is off syllabus. Too hard. But just, if you had to say something, changes the spin state of a particle, a nucleon. End of story. Whatever the hell that means, that's just vomit, isn't it? So to me, not very relevant, shouldn't be a question. On the other hand, the IR. What is the IR doing? So many students pick up the wrong idea. They think it causes the molecule to vibrate. How many people think IR causes the molecule to vibrate? Because every student who said that did not get the mark. What does the IR do? It changes the vibrational state. What the hell does that mean? Well, maybe we need to go and just have a quick look at Wikipedia on infrared spectroscopy. Flip down a little bit. There's a couple of gorgeous little things here. There's a molecule vibrating. It's already vibrating. The IR will change something to do with its vibration. It's not going to cause it to vibrate. And if that looks pretty cute, don't try to imagine what methanol would look like. Old formaldehyde, when you've got these in-out motions, it can be very pornographic. Never mind, we won't go there. We'll go to the more fun ones. These are the sorts of vibrational states that you're changing, right? So we can do some molecular Pilates here. Everyone do some symmetrical stretching. And then fire yourself with some IR, and maybe you change the amplitude of the symmetrical stretch. Or you might do some scissoring. Yeah, you're at the footy, yeah, or the pop concert. Yeah, scissoring. When you change the But it's quantized. You just don't go slowly from one to the other. It's from this or this, but nothing in between. Yeah, but you're changing something to do with the vibration. Rocking, look, you can have real fun with this. I love this website. So just Google IR spectroscopy and that'll come up. But the guts of it, having understood that it's doing something to that, you don't have to know what sort of vibration it's changing, you don't know what it's doing to it, you just have to interpret the spectrum, and I would always recommend, and I've lost it again, let's find it again, pick it up, get my mouse. All right, an alcohol, an OH alcohol, always call it an OH bracket alcohol, is a really distinctive shape. Don't even have to look at the data book. It's somewhere around 3300. Commit that to memory. It's a nice smooth bottom, comes up again, and then jots down again for the CH. CH isn't very helpful. Virtually all molecules have CH, but this is useful information. Ooh, my molecule's got an OH alcohol in it. That is quite a different shape from an OH acid. Don't have to memorise it. It's a little bit to the right, so it's going to be about 3,000, 3,100. Tell that from the data book, but it's such a broad peak, and it's so broad, comes down pretty smooth, may have a sharp bottom, but it definitely comes down smooth, comes up, and then jaggedy, jaggedy, jaggedy as it goes up towards its top. You can't miss it. Memorise the shape. The OH acid absolutely stands out. Can't miss it. Oh, there's an OH acid. And then you'll have a backup. If it is OH acid, it'll also have a C double bond O sword. This massive sword at about 1750, plunging down, right, is a dead giveaway for a C double bond O. Now, an ester will have a C double bond O, but won't have that OH acid. And that's really useful because you'll get lots of molecules that have two O's. A molecule that's got two O's is almost certainly an ester or an acid, and the IR just makes it so easy to pick between them. Just make sure you can do that, because that's sexy. They love getting you to pick between acids and esters, molecules that have two O's. Could be a diol, not likely. They're not likely to give you a diol. It's probably either an ester or an acid if it's got two O's. Don't even look at the fingerprint. The fingerprint is for your computer. Your computer has a database. It can recognise the fingerprint and say, ooh, that's ethanol. You are not expected to memorise anything. You are not expected to find anything there. So a C bond is in there somewhere, don't care. A C single bond O is in there somewhere, don't care. A CCl will be in there somewhere, don't care. If you can find it, good luck to you. You will never be asked to find anything in the fingerprint. That's why I say find the 1500, get out your ruler, put a big rule up there and ignore anything to the right. Useless. Yep, that's for the computer. On the other hand, just recently, because of the amides, NH2s are very distinctive if they're there. And if you look at enough amines, sometimes they're there and sometimes they aren't. It seems a bit hit and miss with amines, but gee, if you see them, those fangs are an absolute giveaway for an NH2. Check the data book, it's at about 3,400. Fangs in both an amine or an amide, can't miss it, that's an NH2. Keep on rocking. NMR, 4 peaks in a carbon NMR, 4 carbon environments, end of story. With HNMR, okay, I reckon if you really studied ethyl ethanoate, it's already been on a VCAR exam a few years ago, but maybe it's about due for a revision. That is such a classic HNMR. Everything you could possibly want to know about HNMR is in. I've got still got 5 minutes, haven't I? Yeah. All right, so I'm going to have to keep rocking, but why does this hydrogen environment split into a triplet? Why does this hydrogen environment split into a quartet? Why is this not split? Why is it a singlet? All right. I used to be able to say you are not going to get multiplets, and I am wrong because the Northern Hemisphere timetable had a multiplet. But VCAR fudged it. You'll be annoyed when you see this year's Northern Hemisphere timetable. And incidentally, please make sure you've checked with your teacher. A lot of your teachers will want you to do VCAR exams under test conditions. and you don't want to have seen them beforehand. Would that make sense? Please make sure you don't go looking until you know you're in SWATFAC. You've finished school and your teacher isn't giving you any more work. If they haven't already given it to you in hard copy, then and only then go to the VCAR website, but you'll be annoyed by the Northern Hemisphere timetable exam. Its spectroscopy is very naughty. If you knew too much, you might have been confused. But come back. So I've thrown in a mystery molecule there. That's probably a little bit more challenging. I threw it in because it's a situation where you just might have to go to the NMR shift data in your data book. A lot of schools seem to teach that as the first place you go. No, you almost never need to look at the NMR shift data in your data book. That's a last resort when you've got two molecules you can't quite pick between. This will be one of those. You should be able to come up with two possible answers that would explain all those spectra, and you would need to go to your data book to compare shifts for a couple of the peaks that you're seeing there and where their shift is in the HNMR to just see, oh yeah, that would have had to be caused by this molecule because that molecule couldn't cause it. But can I just quickly fly through the list in 2 minutes? All right, so I'll leave that with you. I won't even tell you it's up the back of the book, but try that one. That's probably a little bit harder than I would expect on the exam. Won't hurt Kwongers to try that. All right, volumetric analysis, definitely. Look, I'll just mention this last dot point. There's an answer up the back, but I would guarantee, if it's such a logical question, booze has to have the percent volume alcohol content. It's actually ethanol, but they call it alcohol, percent volume. Is that a common unit in chemistry labs? No, we use mole per litre. Could you see a question where they give you the percent volume, and they say, and what's that in mole per litre? They would have to give you the density of ethanol, but that is soluble. And if you haven't practiced that in class, it's never been on a VCAR exam. I wait in hope, in anxious hope, that someday they'll have the brains to do the obvious, because my students will be able to do it. Will you be able to do it? Don't pack up quite yet. Indicators for volumetric analysis. How do you choose an indicator? You've got a whole lot of indicators in your data book. They hopefully will give you a pH curve. The equivalence point is the stationary point, the point of inflection, what do you call it in math methods? Yep. So you just find the pH and choose an indicator that's going to change colour there. Amino acids, proteins. But just back to the amino acids. You've got a whole lot of amino acids in the data book. Most proteins are far too complicated to do anything with, so they're looking for bite-sized little questions. A fairly obvious bite-sized question that has come up once or twice: can you give the molecular formula of one of the amino acids? The obvious, the hardest ones are the ones that have got ring structures. So I'd practice them. There are the three hardest: histidine, proline, tryptophan. So answers are at the back. Or here's another typical question. Here's a section of a polypeptide. What are the names of the amino acids in that polypeptide? Check that out. Primary, secondary, tertiary. Do you love the analogy of the old landline phone cords to give you the analogy for primary, secondary, tertiary? Carbohydrates are annoying, but ether links. Ether links, biologists call them glycosidic links. Don't spell it wrong or you'll be marked wrong. Ether will always be acceptable. It's an ether functional group. Call it an ether link. It's much easier to spell. Just don't confuse it with an ester link. Okay. Fatty acids. You've got a whole lot in the data book. Make sure you can tell whether they're saturated, unsaturated or polyunsaturated. Hopefully you can do that from the formula. Make sure you can definitely, that's often asked, can you turn glycerol and one of the fatty acids in the data book into a triglyceride? It's another condensation reaction. And can you hydrolyse it? Do you understand the significance of a cis? And it is cis. If you've got an unsaturated, then it puts a kink in the chain. How does that affect the melting point? And they're nearly there, hang in there. Enzymes, that's lock and key, we haven't got time for, but that's all key knowledge. Induced fit, that's key knowledge. And then there's just this little diagram of the biologists often get. And biologists always know what happens here, the enzymes being natured. This is what biologists always say for when they're asked for, and why is the rate low here? Oh, because it's lower than the optimum temperature. That is never acceptable in a chemistry exam. Why is the rate lower here? Because the temperature's lower and most reactions go slower at a lower temperature. It's nothing to do with the catalyst. The catalyst is working fine. All right, so it's nothing to do with the optimum temperature of the catalyst. On the other hand, Chemistry 2 has got the maths wrong. I bet the other textbooks have as well. Check that question, see what you think the answer is, and then check my answer. I don't think it'll come up on the exam. I have spooked VCAR, I hope. And if it was on the exam, because I haven't spooked them, then pretty much anything you give will be acceptable because the textbook answer is mathematically invalid. Discuss it with your teacher. So with no minutes to go, I'll just leave you with a thought for schoolies. Please, please, of all the chemicals you could put inside you, do not pay a criminal for mind-altering drugs. If you want to use a mind-altering drug on schoolies, please use ethanol. At least you know it's got a quality control. But that graph should remind you it is actually causes more harm than all those other nasties your parents talk to you about. All right? So your parents will be telling you, oh, don't touch drugs, and then they go, right? Bloody hypocrites. Look at that graph and think seriously about abusing ethanol on schoolies. Look after yourselves. Have a good exam. Have a great schoolies. Enjoy.